Hello, ladies and gentlemen. Welcome to our new lecture for base and data analytics, and our topic will be exploring distributions. Sorry, I am trying to have mic monitoring, but internet is so delayed that I just can't work with that. So we'll return to that idea maybe some other time. I will be switching my PC soon, so we'll see how it works. Today we'll continue the aspects that were happening on last courses and also on the last lecture, and partially things that we've mentioned on the exercises. First questions to everyone: can you hear me? And is everything working? Because I'm trying to use the noise filter to remove the noises that were present previously, but I'm not sure does it work, and am I fully and I'm fully hearable or not. So please answer on the chat. I'm waiting, and we'll start in a moment fully. I see that 6 people are watching, so maybe someone can respond. Okay, great. Thanks, Miss Carolina. What we'll be talking today is generally what we have to do in any kind of Bayesian computation, because our first few lectures will focus on how to do what we will be supposed to do, and later we'll be working with creation of models. So, without further ado, let's start with expectations, because generally, from what we are really doing is that as we mentioned before, the perfect situation would be that we could be considering entire distributions, but in practice, we will be want to get some kind of numbers, because people prefer numbers, and generally we will be computing expectations or expected values from certain functions of parameters of our models. Those can be more complicated functions or less. They can be infinite or infinite dimensional. And it does not only is an expected value of distribution, but also can be an expected value of certain function of parameters. And this can cover almost all kinds of statistics that are present in computation, and it has many beneficial properties, because generally expected values of certain functions are usually the best method of determining the such values for in Bayesian framework. The expectation of posterior distribution is in many senses optimal for computation. So in general, we will be focusing on certain function of parameters, parameters q to be f, and we will be considering its expectation with respect to certain probability distribution or mass function in discrete case of q. So q is distributed according to function pi of q, and its expectation is given by the following integral. This integral might be a bit strange notation for you. We are integrating over all possible values of q, and we are integrating over dq over all the elements in this. So this notation of dq of d something before the integrands is more common in statistical literature. That's why we are using it. Generally, it doesn't change much, especially that if you remember from analysis, the dq is really multiplied by itself, because, for example, when changing variables, we were able to switch them. So this situation is should be relatively clear for you. That kind of integral we'll be considering. So expected value of f is an integral of f times probability distribution of q by q over the entire domain of q. And in discrete case, just we are summing over all possible q values of probability mass functions multiplied by values of this function of interest at q. So like some formulas, not especially difficult ones. And how to compute expectation? And this is a problem, because generally integrals in the in computation of Bayesian statistics, we have a lot of integrals, and integrals, except very basic problems of one variable, are not computable. Because if you remember again from analysis course on your bachelor studies, then there was a substantial issue of finding analytic formula for certain integrals. Either those formulas, either you had to know certain substitution, or the general algorithm led to very complicated formulas on spanning multiple pages, or stuff of differentiation is easy, integration is hard. Generally, that's so. Analytic integration is impossible, so we are left with quadratures. So, for example, we can use Euler Quadrature, so we can divide our probability interval in the to the following form. That is, we find points in the parameter space Qn, and we have their distance between them in order to compute the average, or the sum of all those parameters in multiplied by the distances between them. So the most basic quadrature, not very efficient. There are more efficient ways, but we won't be discussing here, because generally quadratures are problematic outside of one dimension. If there are multiple dimensions, quadratures are problematic anyway. So different option of computing expectations is using the so-called perfect sampling. And in this way, we can obtain a Monte Carlo estimators. Monte Carlo estimators, named after the famous casinos of Monte Carlo, are based on the idea that if we can get the perfect sampling is defined this way, that estimator consisting of average of randomly selected points from Qn that are distributed as the distribution pi will asymptotically converge to the expectation of f. So if we can generate set of samples according to our distribution pi coming from Q, that and we can compute their average, then this average should converge to the expectation of f. And this procedure will potentially allow us to compute the value. So this is nice. And what is especially nice is that computing expectation is a variable that is a sum of random variables. For sums of random variables, we have the law of large numbers, and we have central limit theorem, and central limit theorem says that variable that is a sum of identically distributed variables, and expectation is and the mean is exactly that, is normally distributed, and this normal distribution has the expected value of equal to, in this case, to expectation, and has a standard error given by square root of variance of f with respect to distribution pi divided by the number of samples. So this is a good information, because we have automatically bounds for our computation. We have some kind of error measure. We do not have to have infinite number of samples. We can know what happens in limits of samples. So this is a good advantage. So let's go back to our motivational example from Mass Effect. That is, we are scanning a planet, we are looking for water, and we are using our probe that we'll be finding here. So when we compute that, when we analyze this planet, we get some kind of results. And we will be using the most basic way of analyzing it, that we will be able to cover both quadratures and sampling, which will be grid approximation. Grid approximation is not something that we can use in practice, but for this case is absolutely enough. So generally, grid approximation is like this. We divide our parameter space into a grid. So we find how many points we used to estimate in the posterior, and we take our parameter values on this grid. So this is generally the idea, that we are transforming our continuous distribution to a discrete distribution, which makes everything much easier. Then we compute values of the prior at each parameter value on the grid. Then we compute the likelihood at each parameter the value. So we have values at certain points, and we compute the unstandardized posterior at each parameter value. So we compute the value that is proportional to the posterior, because we multiply the prior and the likelihood. In order to get it normalized, we would usually need to also have the probabilities of all the possible cases. But in this case, we just make it much easier. We standardize our posterior, because our posterior will become a sequence of discrete values corresponding to our grid. So if it would be a probability distribution, sum of all those values would be equal to 1. So if we compute, we sum all the variables of our posterior, then we can divide the sum, so it will become a probability distribution on the grid. We transform our infinite set that consists of an infinite number of points, because it was a continuous set, into a grid, and we establish a probability distribution on that grid. So from the continuous distribution on an interval, we go to a discrete distribution on the grid. So generally, that is very simple. And we can do it with some code. And this code is given by the following form. I'm not sure that I've run the code yet, so maybe I'll just run everything for posteriority, just in case that everything will work. And let's come back to our approximation code. So it's running, because I'm not sure that all the packages were running and stuff like that. So we define our posterior grid approximation as a function that has 5 points on the grid. We define number of points on the grid, we defined number of successes, and we define the n, so number of experiments. So instead of successes and failures, we just define the success and the n. Success, of course, is finding water. Failure is not finding water. And we get the something has broken. Something has broken. Like, very nice. Oh, I don't have one package installed. Sorry, I need to correct that. This is the... So as you see, everything is live here. Everything is going smoothly, but that shouldn't make us much easier. Okay. We just need to install one more package. That's the problem with multiple repositories on multiple computers, that not everything is running completely. Okay, now it should work. I need to restart kernel, of course. Okay, I think I'm done here or not. Yes. Now it's running. So let's come back to our code. Hopefully everything will work. So returning to the idea. So we have our function. We define a function that will perform posterior grid approximation for our. Will create posterior grid approximation for our problem. In order to do so, we need to define the grid consisting of number of grid points, which we'll do during linear realization. Then we need to define the prior. At first, we'll just use uniform prior, which will. Oh, that's why he's 5 here. Okay. So in order to everything would be fit for that. Okay. Then some hard coding, but still it's not that. This is really doesn't matter because we are standardizing at the end anyway. Then we compute likelihood using binomial distribution, which we use from the stats in SciPy. So we get binomial probability mass function, providing number of successes, number of tosses, and values on the grid. So it computes for all of those probabilities. Then we compute the unstandardized posterior. So we multiply the likelihood times the prior, and then we compute the posterior by we standardize the posterior by dividing the unstandardized posterior by the sum of all these values. So now it will sum up to 1, and this function will return the grid points that we have and posterior. We need grid points in order to plot everything. So as you can see, for 5 points, calling with default parameters, we get 5 points with appropriate values at the certain points, which, as you can see, 0 was being rounded. Values at the edges are being rounded. Okay. So how such approximation would look like? Well, for 5 points, it will look like this. For 20 points, it will be much smoother. Again, like with any kind of computation, for example, in MATLAB. What is important, as you can see here, we don't have numbers here. Why? Because we have different normalization. In order to get all those sum to 1 and those sum to 1, we have to divide them by different numbers. So those values here will be larger than those here. Here we have 20 points that have to sum to 1. We have 5 points that have to sum to 1. So having 5 points sum to 1, those values will certainly be larger than in case of those. So values here do not correspond to values here numerically. It just gives us the distribution of where is the most probability here. Okay. So generally, in order to get the information, even about complicated posteriors, is to just simulate the data that corresponds to that and get parameters estimates from sampling. So generally what we'll be doing will be sampling from the distribution and computing the parameter problems. How to do sampling for a single parameter problems? The easiest way is to use the inverse cumulative distribution function. What does it mean? We compute the cumulative distribution function. That is the function that for each value of the parameter, it assigns the value of between 0 and 1 corresponding to the probability of random variable taking a value that number or less. And inverse is a mapping from 0 and 1 to the entire range of parameters. So inverse cumulative distribution function can be then used with random number generator on uniform scale. So using uniform numbers from between 0 and 1, we can transform those numbers into the values of parameters on our grid. Grid approximation, on the other hand, is a bit more universal because it does not require from us to compute the cumulative distribution function. In a way, it just allows us to compute stuff using the values from the grid. So let's get a bit more advanced option in order to analyze different priors for our use, and we'll modify our function slightly in order to allow us to use the uniform prior, the truncated prior, so the prior that gives us that assigns all the probability below 0.5 equal to 0, or double exponential prior. That will be a prior that sets the value on a median. We propose here free rest is exactly the same as previously. We standardize everything. So what we are doing here now, we can now plot our probabilities. So we can assign compute both prior and posterior depending on which method we use. If you want to use uniform, it will look like this. So we have uniform prior, and posterior looks like this, similar to, it generally is a beta distribution. If we change to truncated prior, it will be cut off here, the same as the prior being cut, the posterior will also be cut here. And if you want to use double exponential, it will do like this. So we just compute the values from the posterior and the prior using the same function. Why? Because our function, if we assign both zeros to number of successes and number of tosses, it will just reduce itself to being just the prior. As we can see here, the likelihood will be always equal to a constant number when those values will be equal to 0. So let's return first to the uniform variant, and let's perform our sampling. What you can see here is a so-called good practice in random computation. We assign the seed to the random number generator. Why we do that? We do that in order to be able to replicate our work. We want to replicate our simulations for what is going on, what was happening. Thanks to that, we will be able to, if something goes wrong, we'll find what was the reason. Was it a random situation, random happenstance, or there is a problem in our model that we need to identify, and we'll be able to find it only through returning to the our experiment again. How to create samples? Well, here will be much easier situation because we'll be using random sampling with replacement, which generally is like this. This function looks like this. We sample values from peg-grids, so the values of possible parameters. We do it 1000 times. We do it with replacements, and probability of each of the points on the grid is determined by the posterior, so the value that we had before. And the having that, we have the we can compute the values properly. This is actually not needed here. I'm not sure why it's here. So using that, we get 10,000 values of theta, and those values are being randomly sampled from our distribution, and they look like this, which of course is not very clear but we can use a histogram in order to present what we have here. So again, here we use density histogram with density parameter, so it can consider it as a value of as a probability distribution. So as we can see, the samples from posterior generally are consistent with the posterior. The histogram is consistent with what we expected it to be. But now we have samples on which we can compute multiple statistics. For example, in order to compute the probability of if p is less than 0.5, we just need to sum over all the posterior values that correspond to such values of p. We can do it either by integration from a posterior or just by computing samples less than 0.5 and computing the average. We had 10,000 samples, so we divided by 10,000. Just to be clear, those values are of course consistent with one another. The difference is that we have different posterior at different places and different samples. We can the same way use to compute the intervals of interest. For example, find what is the probability that samples are between 1/2 and 0.75. So again, we compute that, and we can of course compute the quantiles the same way. So generally, we've reduced the problem of integration to the problem of performing statistical operations on a set of samples which we generated by random sampling. So this is a good thing. So having such good thing, what is it? The more interesting, we will be using the same procedure all over again in other problems. We will be avoiding the integration issues by moving to sampling. So having that, we are able to compute the prior predictive distribution, and this prior predictive distribution says us how it's using this situation. Remember, prior predictive distribution is what we know before before data, and posterior predictive distribution is what we know after data. So using prior predictive distribution, setting prior in this case, which was the uniform prior, we are able to establish the rate of the success, or so we can observe what kind of data can we expect. And our model says us that we expect that the outcome of our model will be either 0 and 1 with half probability. How we do it? We again assign the values on the grid, probability, but this time we don't assign the posterior, but we assign the prior. This is right posterior, but it's our function. We are using, of course, the zeros here. Here, actually, there should be prior. That would be more. That would be more clear for the readers. So as you can see, we are sampling from prior and getting value. So prior predictive distribution, if you remember, was like this: we sample values of parameters from prior, then we feed them to the likelihood, and using likelihood we sample values of the output. So we are estimating, we are predicting the output based on measurements based on our prior information, because in likelihood we don't have any data. In case of posterior predictive distribution, then we have situation that we can provide our model with the data. So we've provided with extra information of that we have, in this case, 6 successes in 9 tosses, and we can compute the mean rate of success. So we predict that in 64 cases, 64% cases, we will receive the outcome 1. Sorry, we will find water from the data that we have, and the samples are corresponding to that. Then more of them are in 1 than 0. So this is of course for only one of the priors. If we change the prior to the truncated one, so we assume that there is at least half of the water on the planet. So our posteriors look like this. And we can sample here. Now it's only samples values above 1/2. Histogram of which is consistent because also it cuts off at 1/2. Then the probability of oh, this is something that I'm actually surprised by, because it should be 0 and it's not. This is interesting, why it's not working. Posterior is defined here by grid approximation with wrong, of course. This shouldn't be here. That would be much better. In this case, sorry. Again, not enough testing. Okay, this is okay. So we have the now the posterior probability is equal to 0, which is consistent with our sampling because samples also are not equal to 0. Now probability of inclusion between 0.5 and 0.75 is much larger. Quantiles are the 90% of samples are between, actually it's 80% percent of samples are between 0.54 and 0.82. Our prior gives us is still with wrong prior. Again, this is something I think we should just remove from here, and I think will be much better, because here we have the prior assigned and we just don't repeat it here. So as you can see, our prior now says that if probability has at least 1/2, it cannot be less than half, so our mean rate of success will be 75, and we expect results like this, that we have three times as many ones than zeros, which is large advantage. This is what our prior predictive distribution is for. We see what's our knowledge that we used before, what our prior gives us to expect. What can we expect that will happen? And from our posterior predictive distribution, which also should not be here, but I'll just replace it with this one for a second, so we don't have to come back again. And here, actually, the data is not as consistent because our mean rate of success is only 68%. So our data says that it's not as favorable values as our prior suggests, so we are moving away from that. And again, we have the histogram of the same. If we moved finally to the exponential distribution for prior, this is of course the same situation. So this is generally a procedure. We use prior predictive distribution to test our assumptions about the prior, and then to verify is our posterior consistent with observed data. So as you can see, the distribution now becomes a bit more skewed. It still takes value from 0.2 to 0.9, but it's a bit more mass is oriented for higher values. Histogram is consistent with what we observe, so our sampling generally works with distribution. This is not something that we'll be able to check usually with our work later, because this is not something that really happens, that we can observe the posterior distribution and see how it will look like. So we won't be able to compare that, but this gives us a bit of confidence in our sampling. And computing the appropriate values, so now we can again compute here with the integration with Euler method, and here just by sampling from 10,000 samples. We get values from 10,000 samples is very well. We compute the intervals of interest, and we can compute our quantiles, which are generally similar to the uniform distribution. The prior, in case of prior, we had a bit of advantage for the more ones, but this is very limited. So again, prior is relatively flat for the entire interval, and in case of posterior, our data suggests that there is an advantage, but not as big, and we can look at it from the posterior distribution, that posterior is not as well defined, it is much more thicker than in case of uniform in this case, because it gives us the it gives us less conservative values. Why? Because our prior generally suggests that values should be around one half. There are some tails here and here, but most is here. So here is the assumptions in the prior that probably it's somewhere around 0.5, and that makes our prediction skewed in that way. Okay. Okay, this is not that important. Okay, so generally, question becomes, do grid approximation generalize well? And it depends, because there are cases when we can, for example, increasing dimension, we can see that grid approximation can cover the distribution well. The problem is that, of course, that there are a lot of zeros here, for which we still need to compute values, and so that might be inefficient. But generally, what we are going to do here is that we can sample values in, we can compute values of the integrals on this grid. But if geometry becomes a bit more complicated, it might happen that most of our values will just be outside of the grid, or very tangentially connected to the grid, and that would make it much more complicated in order to evaluate on the grid. So generally, grids are nice toy that we could use before, but they are not groundbreaking stuff that we will be able to use for the computation, and we will have to look for something else. So the question is generally, what contributes to expectation? And the problem is that here is where our intuition will fail us, because when we think about computing an integral, we think that the most important is the function that we are integrating over. So we are mostly interested in the p function, the probability function. Why? Because this function will have large values around places where q is probable, and will be small anywhere else. So assigning that will the further we are from the maximum value of the function, the more distribution will be flat. Why? Because our distribution needs to integrate to 1. So if it has some values around the maximum, the rest has to be sufficiently flat in order to such integration would be possible. So when we are computing an expectation, we will think that the values inside the integral, the most contributing factor is dq. And so this is something that we are, let's say, intuitively based from computation. For example, when we are analytically computing the definite integrals, when we had the value, the function that was vanishing on certain intervals, we were just cutting the interval in pieces from the and leave only places where the subintegral function is not 0. The problem is that in most cases we have this tail behavior that we are not 0 but close to 0, and unfortunately we cannot usually avoid that, because the problem is with the volume. Because the one part that we usually treat as a decoration in the integral is dq. And dq is not a decoration. dq is the volume over which we are integrating. Because it takes, in case of one variable, everything is very simple. When we divide our interval to 3 parts, we can assume that if the maximum is in the middle parts, focusing integration on the middle part, wouldn't introduce any errors because in those parts we have equal to 0. So if we compute in 1/3 of the interval, everything will be okay. Unfortunately, when additional dimensions arrive, we have some problems. Because if we focus, for example, on a box of space of like a square, and we take a middle of it, then we do not only ignore the part on the left and the right, and part on the bottom and on the top, but also parts in the corners. So this causes that this part here took only 1/3, focused only 1/3 of our function, 1/3 of our volume. In this case, this square in the middle is only 1/9 of this volume. So increasing a dimension reduces our contribution of the parts around the maximum. And if we go to third dimension, then again we have both sides, on the left, on the right, top, bottom, front and back, and again, and again, and then our middle cube, consisting of values of close to maximum, becomes 1/27. So increasing the dimensions reduces the contribution of the entire area around the maximum to the volume of the parameter space. So increasing dimensions causes that the distribution will behave not only near to maximum but also everywhere else. So in this case, we have a problem that volume rises exponentially with dimension. Our function is large next to maximum and then starts to drop. However, the volume over which those dropping factors happen are actually rising, and the further we are from the maximum, the more we have, because if we look our cubes, if we have to look another step of the cubes in here, so we will have much more elements, and in 3D even more. So all those parts will be encapsulating more and more and more. So we have a lot of volume and we have small values of pi, small values, but we'll have a lot of them because it will correspond for each element of the volume. So because of that, this increasing volume will be problematic. Of course, if pi vanishes somewhere, then okay, no problem. But distributions rarely vanish. Distributions usually have tails. So they allow the possibility of something unlikely happening. In Gaussian case, it's very unlikely, but in more robust concepts, there's no problem of, there are so-called heavy tails, which causes you to think everything twice. So, if volume rises exponentially with dimensions, then what we can do? Well, we are not computing volume by itself. We are not computing function by itself. We compute the product. And the product is something that counts, but because these products show us that while we are increasing dimension, the main elements that contribute to the expectation is this set where volume is rising, but distribution has not vanished before. So we have a lot of DQs, a lot of volume, but but not negligible values of pi. So here are those values that are completely negligible, so they can cancel almost everything, generally essentially 0. But here is this not that this product is not zero and it dominates the IQ. So initially, while values of distribution are very high or relatively high, the volume is minimal. The volume is very insignificant, so this product reduces to zero. Here, while the volume is, there's a lot of volume, we are so far in details of distribution that they are just zero. So we have a middle ground, the situation when this product takes values that are non-zero and are contributing the most to the expectation. Because again, we want to compute the expectation, and this expectation will consist of the integral of this entire product, and most of the integration is here in this area, the area which is called a typical set. Typical set is a set in the space of parameters where the most probability needed for computing expectation is. So here the product of dq times s by q, its sum is the biggest. So there, the cumulative volume times the probability is takes most. Of course, there is no such thing like definite boundary of where typical set starts and ends with respect to that, because we have a multidimensional integration, but we generally have a intuition what it is. This the values in the typical set contributes to the expectation, and because of that, we have something that is called concentration of measure. Because generally, typical set will be something that is, let's say, a fuzzy surface, a surface with or a manifold in parameter space that does not have a clearly defined boundary because it's regards probability distribution, but there are the points that will contribute much. However, there is something called concentration of measure. And concentration of measure generally causes the fact that because Q is rising, the location of typical set is being moved away from the mean. But on the other hand, it is being tightened by dropping values of probability distribution. So that situation that typical set moves away from the mode, the middle of the distribution, and becomes much more thinner. So that makes its analysis more difficult. And typical set is the most important for us, because only by values from typical set we'll be able to compute expectations, either through integration, because we would have to integrate over typical set to get a good estimate of expectation, or by sampling. Again, we need to sample from the typical set to get the results. So now we need to find a way in order to sample values from the typical set. And sampling values from the typical sets is a partially challenging proposition over which we will be discussing now. So generally, there are multiple ways of doing probabilistic computing. All of them generally focus on getting some kind of estimate of parameters through expectations and with or not. And we'll discuss briefly some of them. Give you some kind of spoiler. Our main focus generally will be Markov chain Monte Carlo, over which we will discuss next week in more detail about parameters. Today we'll just highlight the ideas that are in the methods of exploring a typical set and exploring the distribution, and probably we'll end a bit earlier than usually. Okay, let's start with the staple of frequency statistics or classical statistics, the model estimators. Generally, we want to approximate our expected value using the value of the maximum of the distribution. So we want to find a point that corresponds to the maximum of the distribution. And in a situation when we have a lot of centrality in our distribution, it is kinda normal-like, then mode and expectation coincide. And if they coincide, then our maximum is very close to the value that we are actually interested in. And this is profit. The issue is that, however, that if distribution is skewed in some way, like for example the one we had before, then the maximum might be far away from the expectation, from the expected value, and it can even be very far. So first of all, those points are not inside the typical set, but that's, well, not the problem. But the second is like finding those skewed distribution will have the expectation moved. And also, by computing the mode by itself, we only have one parameter, one value. What with the uncertainty, how to capture that? The methods of model estimation are not interested in the typical set, so they do not have any information about the uncertainty, because it doesn't provide us with appropriate results. We don't have samples from the typical set, so those values that are contributing. The more advanced idea is the so-called Laplace Estimator, which is based on approximating our distribution with a Gaussian distribution. Gaussian distribution is a very nice property. First of all, it is very easy to compute the expectation of multiple functions for that, because it is either by so-called Gaussian integrals for certain types of functions, or just by appropriate application of numerical methods, because those are very well behaved functions. The idea of creating Laplace approximation is that we need to again find the maximum of our distribution. Then, in that maximum, we know that because it's a maximum, the Hessian function is negative definite, and because of that, we can construct the approximation to our distribution by a normal distribution, where mean is the location of the maximum, and covariance matrix is given by the matrix of second derivatives of the distribution function in that point. So it is essentially an extension of our posterior with a Taylor approximation around its maximum. And of course, this is relatively easy proposition if you are able to compute second derivatives. And again, if our distribution is relatively close to Gaussian, we are in a very good situation, because mean of our distribution generally will be coinciding with mode in some way, and we have a relatively good exploration of the typical set. Our Gaussian model, which will have typical set always in the form of ellipses, because it cannot happen in another way, because it's extends by it's a contour set, and they are coincide a bit, so it will be okay. However, if our distribution is very non-Gaussian, so the generally means that its second order Taylor approximation around the maximum will be of low quality, then unfortunately we won't be able to use this method efficiently. And this method, however, has proponents. First of all, in McElrath's books, Statistical Rethinking, there's an R package for that book, which contains one of the methods that are there is the methods based on computing the Laplace approximation for Bayesian models, and it can work if the model is not very strange. This approximation can work. And also there is a numerical package for R called INLA, which is called Integrated Nested Laplace Approximations, which is an algorithm allowing very efficient computation, in which the a Laplace approximation is being used to certain elements of the probability distribution that is being considered. Actually, it's certain marginal distributions, and then such automated thing gives you very fast results, which can be much faster than Monte Carlo simulation. The different way of computing some kind of approximated methods is the variational approximation. Variational approximation is a relatively popular algorithm allowing to sample from the posterior distribution. The idea of variational approximation is that we don't know how to sample from our proposal, our posterior distribution, but we have a collection, let's say a family of functions that we know how to sample. So let us approximate our posterior with a sum of such functions with certain coefficients. So we reformulate it to a problem of optimization. This is an variational optimization because we are optimizing functions. We are trying to find a function that solves our problem, and in order to do so, we are minimizing something that is called usually Kullback-Leibler divergence, or divergence function, which generally says how much two probability distribution differ between one another. And in practice, it is done actually not by minimizing the distribution directly, but rather minimizing its certain bound that allows computation to be much more efficient. And variational approximation has multiple advocates because variational approximation can be very fast. It can be very fast because it reduces the problem of sampling to a problem of optimization, which is deterministic problem. So there might be some issues, but which we mentioned in a moment. And second, it can handle problems with a lot of data, which can be problematic for probabilistic computation of different kinds, that this can work well, at least fast in such situation. Unfortunately, there are some problems, because variational approximation is an optimization problem, and it's not necessarily well-posed problem, or at least not convex problem. It is not a situation that for all proposal families of variational families of functions in order to create approximation. It's not every of them distribution can be expanded, or this expansion is any useful. Also, for example, here we can see that there is a certain similarity of difference between these three ellipses for our typical set, and because of that, neighborhoods of each of those will have similar values, which might need to solving the problem of multiple minima, because in such situation multiple distribution will fit it similarly well, and there will be a much difference between them. If they would be close to each other, there's no problem, because there is something that will be a global minimum in between them. However, if there are three which are significantly different and qualitatively and have similar divergences, then we have a multimodal problem that can be very difficult to compute. So that's the one problem, that we might get stuck in a local minimum and not be able to find global one, which can be very difficult later in model use. And the other thing is that, unfortunately, variational approximation not necessarily can capture well the complex typical sets. Either they can do it by overfitting the typical sets, so getting much larger typical sets than the actual set of our distribution, which causes our inferences to be much more uncertain, or opposite, it can be much more concentrated and give us certainty that is not justified. So generally, what is left? Well, like, all those methods have their benefits. The variational is very popular because it can be fast. Laplace is computationally fast and is also conceptually very easy to understand. The case of Monte Carlo is a bit more difficult because people don't really work with chance that well, at least people's mind. So we will want to get samples from our typical sets, so get some values from that. And it's not that easy because it's not easy to draw samples from any distribution. Usually this distribution has to be known up front. Because if it's something is normal or low dimensional, we can do anything. If it's one dimensional, we can just compute the inverse or grid or something. In case it's high dimensional, there are a lot of problems. And when and generating samples, especially from complicated, the distributions might be very, very difficult. And generally, despite the fact that we know what we should get, it's not that simple to do. One of the ideas to make it work is so-called importance sampling, in case that you can sample from something that you know and it's easy to sample, and then introduce approach corrections with so-called importance weights. The problem is that this strongly depends on the quality of this proposal distribution, which will be generating samples from, and finding a good proposal distribution might be very difficult in high dimension, because those typical sets becoming very thin and any difference can result in different typical sets. Finally, the backbone of current statistical computation, which we just only highlight here, the Markov chain Monte Carlo methods. Markov chain Monte Carlo methods is a way of finding the distribution or sampling from the distribution, not by randomly drawing independent samples, but by finding a sequence, a Markov chain of samples that will reach the typical set and stay in there. Those samples will be correlated with each other, which has to be countermanded in some way. But the intent is that if we get into the typical set, then we will stay in it and we'll be able to explore it. And that's how Markov chain Monte Carlo methods work. Next week, we will analyze a most classical algorithm, that is Metropolis Hastings algorithm, and we will and we will finish the discussion with the Hamiltonian Monte Carlo method, which is currently state of the art, the thing that on which Stan and PyMC3 and those Julia frameworks are being built on in order to provide necessary computation. So this will be next week. However, I strongly recommend some extra reading. The popular probabilistic computation case study by Michael Betancourt. This is something that I was extensively using during this. As you can see before, there were some copyright mentions in all those figures because those figures were created by Michael. And I strongly recommend all his work. This is his work is much more detailed than I give here, but will require you a few hours to study it carefully. So this is an optional extra reading for interested people. I can now answer some questions if someone wants something, and if not, we will be finishing. Let's get a 1 minute for questions. Don't be afraid, I'm not biting. Oh, this is the values on the histograms are not probabilities. The constraint to 1 is on the sum of all the values, or on an integral. So it can be a very thin bin in a histogram, which can take a very, very high number. So it can be even in thousands. Just that the sum of the integral of the entire distribution would be equal to 1. So thin bin with very thin bin with large spike value will not be a problem. Generally, distribution can take very large numbers, but their that their integral sums to 1. Of course, this is not for the discrete situations, because in discrete situations we don't have that comfort. In discrete probabilities, you don't have an integral, you just some values. Any other questions? If not, we'll see you next week, and we'll discuss first in the classes. We'll be still fighting with command stan in order to get you familiarized with stan language, and on our lecture we will finish the aspects of Monte Carlo computation and Hamiltonian Monte Carlo in order to know what we are doing. Besides that, we are running things with in stan. Thank you very much for your attention here, to all of initially 11 people, now 8, and for those that will be watching us at different time, have fun. Hopefully you'll learn something. Thank you very much, and goodbye.